Welcome everyone. My name is Kwiatek, and together with Yehuda Ben Zion, we are going to show you the presentation entitled Detection Limits and Near-Field Ground Motions of Fast and Slow-Propagating Earthquakes. Providing theoretical constraints on expected ground motions generated by earthquakes characterized by different static and dynamic source characteristics allows us, first of all, to separate tectonic and anthropogenic seismicity from other sources of weak ground motions. This may be especially useful in automated processings of vast online datasets that do not yet include any validation of the nature of detected seismic sources. It also allows us to optimize seismic network design when in situ information is scarce, and finally this information is relevant for seismic hazard and engineering seismology. In this particular study, we use synthetic seismograms to investigate the theoretical limits on earthquake detection of fast and slow propagating seismic events that occurs in Southern California. We also present the peculiarities of ground motion distribution observed at short epicentral distance from a family of magnitude 6 earthquakes that are characterized by different rupture type, slip velocity, and rupture velocity. In the first part, I will shortly describe the modeling approach. So the full waveform field was generated using discrete wave number method of Poisson. We have a finite fault plane that is defined by length L with W and the double couple source mechanisms. Signal from the source is essentially a superposition of elementary sources that are arranged in a grid over the fault surface. Each elementary source is triggered when the rupture front that you can see here in animation reaches the corresponding grid point. This parameterization in principle needs a triplet of parameters, for example, seismic moment, static stress drop, and rupture velocity, in addition to source kinematics and other algorithm-dependent parameters. The radiated waveforms are subjected to the propagation effects in the crust along the ray path. And to model this, we use the 1D velocity model of Fang et al. And 1D attenuation model of Hauxon and Shearer, both that are valid for the Southern California. Finally, the resulting waveforms were superimposed with the randomly generated noise. And here, we use the noise model that we previously developed in our 2016 study, and it is shown here with the dotted thick line. So at low frequencies, the model was taken as an average of highs and low noise model of Peterson. At high frequencies, we basically use different studies that were available to us, and we average them at this range. Finally, the peak ground velocity as well as the signal-to-noise ratio could have been measured from ground velocity seismograms that were first high-pass filtered. The filter was chosen depending on the magnitude. For the smaller events, we use 1 Hz high-pass filter. For the large earthquakes above magnitude 4, we use 100 seconds as a corner for the filter. The signal-to-noise ratio has been calculated as the ratio between the maximum ground velocity amplitude and one standard deviation of the noise level on the filtered seismogram. Here is an example of earthquake detection limits at 10 kilometers epicentral distance from an earthquake that is occurring at the depth of 8.5 kilometers depth. Curves that you can see here are parameterized by different stress drop values, and they consider P and S waves. So first of all, it is no surprise that the smaller the magnitude is, the lower signal-to-noise ratio is observed. Also, it is not surprised that the detection of earthquakes through P waves only is way more difficult than the detection through S waves, as the latter waves are simply having larger amplitudes. We also quantify the effect of variable stress drop on earthquake detection, and what we found is the lower stress drop results in essentially smaller signal-to-noise ratio. We also investigated the influence of rupture velocity on resulting ground motions. The curves in this plot are parameterized by the different rupture velocity equal to 10%, 50%, and 90% of shear wave velocity. Obviously, lower rupture velocities lead to decrease in ground motions and signal-to-noise ratio. So, for example, for magnitude 4 event that you can see here, the signal-to-noise ratio for S phases is decreased by approximately 40 dB between events characterized by rupture velocity equal to 90% and 10% of shear wave velocity. In the following, we focus on modeling surface distribution of near-field ground motions from a family of exemplary strike-slip magnitude 6 earthquakes. The geometry of the fault that you can see here was specified following the scaling that was developed by Leonard in 2010 for intraplate strike-slip faults. We consider basically multiple rupture scenarios that includes bilateral and unilateral rupture propagation, low and high rupture velocity, and slow and continuous faulting type, this is the crack model, versus transient and fast pulse rupture type. Rupture propagation was either bilateral or unilateral, as it's presented on these two animations. In bilateral case that you can see on the left, rupture starts in the center of the fault and propagates first circularly, and then until it reaches the top and bottom of the fault, and then it propagates bilaterally in each direction along the rupture length. In unilateral case, the rupture starts on the side of the fault, and basically it propagates unilaterally in one direction. Different rupture velocities have been considered in this modeling. In this particular presentation, I will show you two cases where rupture velocity is fast, it's 90% of shear wave velocity, and we also consider a slow propagating dynamic rupture with rupture propagating as 10% of the shear wave speed. Finally, we considered two rupture types. Here I present a schematic animation of anti-shear particle motions on a fault assuming bilateral rupture propagation and so-called crack type rupture. In crack type rupture, each particle on the fault that you can see here is triggered by the propagating rupture front that you can see here with this transparent pinkish surface, and it moves essentially until the rupture front reaches the end of the fault. In this scenario, the rise time is comparable with rupture time, which overall means that low slip velocities are expected here. In pulse type ruptures, particles on the fault are again triggered by the propagating front, as you can see here, but their movement is essentially transient and it is constrained to the limited period of time. And that creates essentially a visible pulse of slip velocity that is propagating along the fault. That is also called sometimes hidden pulse. Ultimately, this type of rupture involves much shorter rise times in comparison to the total rupture time, and overall that results in higher slip velocities. This graph shows the surface distribution of maximum peak ground velocity for the bilateral and unilateral rupture propagation. For reference, the fault surface trace is shown here with a green line, and the rupture directions are shown with arrows. This particular scenario considers high rupture velocity and pulse type ruptures. So what we can clearly see here is the prominent directivity effects. As actually expected, along the rupture propagation directions or direction in unilateral case. Also, what one can see are the very high maximum peak ground velocities that are reaching over 35 centimeters per second. And this is an intrinsic property of high rupture velocity and pulse type ruptures. The second case that you can see here also presents the pulse type rupture, but the rupture velocity has been reduced to 10% of shear wave velocity. And this, as you can see, resulted in a dramatic change in surface distribution of maximum peak ground velocities. Zones with high ground motions are not anymore aligning with the directivity. Instead, they correspond somehow to the radiation pattern that is originating from the assumed strike-slip kinematics of these sources. We also observe a general drop down in the level of ground motions with values now not exceeding 0.2 centimeters per second. In third scenario, we are back to high rupture velocity, that is 90% of shear wave velocity, but we now assume the crack rupture type. So as you can see, the surface distribution of maximum peak ground velocity is now a kind of complicated mixture of directivity effects seen along the preferable rupture direction, as well as earthquake kinematics that is seen as these four lobes at 45 degrees off the fault trace. In the last scenario, we present the case of low rupture velocity and crack type rupture. So this results in lowest ground motions modeled in our study. The surface distribution of maximum peak ground velocity is again dominated only by the earthquake kinematics with no visible directivity effects. I summarize 4 previous slides in a table, and to the right I present also an aggregated picture that presents the maximum ground velocity amplitudes averaged over all azimuths for all models that we considered so far. The table and graphs show that rupture velocity and slip velocity have both a profound effect on the levels of ground motions, with pulse type ruptures that are fast, displaying nearly 4 orders higher ground motions than slow and crack type earthquakes. The observed ranges in ground motions are, of course, very important from the perspective of seismic hazard and the risk assessment, and they are also relevant for the engineering seismology. This information is also relevant for designing and optimizing the seismic network layouts for detecting of slow but still dynamically propagating earthquake. So slow propagating and crack type earthquakes display a different surface distribution of ground motions that essentially coincides with earthquake kinematics. That is fundamentally different than ground motions distribution for fast and pulse type ruptures, where we essentially see the clear accumulation of seismic energy along the rupture propagation. This means that to detect slow and crack type events, we actually should distribute seismic network in such a way that the sensors are located on the slopes that are essentially located 45 degrees of the fault trace. To summarize, in this study, we modeled the influence of source characteristics such as static stress drop, rupture velocity, and rupture type on earthquake detection and resulting ground motions. We showed that apart from earthquake magnitude and associated past effects that guides the rupture propagation, lower stress drops and rupture velocity reduce visibly seismic radiation and increase the minimum magnitude of detection. We highlight the importance of rupture propagation effects for resulting ground motions for large earthquakes. The surface distribution of ground motions depends on rupture velocity, directivity effects, and rupture style that ultimately influence the radiation pattern of seismic waves. Finally, the presented modeling scheme provide useful information for optimization of seismic networks for different types of seismic events and near fault seismic hazard. So with that, I would like to thank you very much for your attention and watching this video. And I am putting here the references to two papers that we published in Journal of Geophysical Research that discusses the detection limits and influence of source parameters on near-field ground motions of various earthquakes. Thank you very much.